everybody. It is a pleasure this afternoon to welcome Sergio Poppi from the INAF Astronomical Observatory of Cagliari for his this virtual colloquium. We were hoping to have Sergio in person today, but sadly, because of the COVID pandemic, we are still not allowed to. A brief introduction to Sergio. Sergio got his degree at the University of Bologna in 1998, and then he had several research grants to work at the Institute of Radio Astronomy in Bologna, and in particular at the beginning of his career he worked on experiments to measure CMB polarization. Since 2006 he joined the SRT, the Sardinia Radio Telescope project, where he has been involved in the control software development and methodology of metrology of the telescope optics. And since 2018 is the head of operation at SRT. Today Sergio will present, will give us a talk about the present and the future of the Sardinia Radio Telescope. So welcome again, Sergio. I give you the time at 40 minutes, so please go on.
Thank you very much, Michele. It's a pleasure for me to being invited to give this talk, and I will talk about what is the Sardinia Radio Telescope and what is going to be. Sardinia Radio Telescope, it's an observing infrastructure operated by INAF, and it is the result of the collaboration, scientific and technical, among the Observatory of Cagliari, the Institute of Radio Astronomy, and also between the Arcetri Astrophysical Observatory. SRT is a 64-meter radio telescope. It is fully steerable, and it is designed to operate at frequency from 300 megahertz up to 116 gigahertz. It has been funded by the Ministry of Research and University, by the Italian Space Agency, and also by the regional government of Sardinia. Just a brief timeline. I just start from when the SRT has become a telescope. So that is from the commissioning, which was from 2012 to 2013, with and its opening ceremony was in September 2013. In February in 2016, the early science program started, and in 2017 we had to stop for the refurbishment of the active surface, and also we had to move into the new buildings and infrastructures. Before then, the control room was inside a container, and also devices were installed in containers. So moving to new infrastructure needed to a new recommissioning, and from December 2018 we started a call for proposal together with Italian radio telescopes. Where is located SRT? SRT is in Pranus Angoli, which is an area 40 kilometers from Cagliari at 650 meters above the sea level. It is also about 40 kilometers from the headquarters of the observatory, which are just nearby the Department of Physics in of the University of Cagliari. The SRT area covers about 14 hectares and includes headquarters, a guest house, a visitor center, and obviously the telescope. It is important to say that INAF manages 3 single-dish radio telescopes, and where observation can be run either in a single-dish mode or in a network for interferometric observations. The 3 telescopes are the SRT, the Medicina Radio Telescope, and the Noto Radio Telescope, which have size of 32 meters of diameter of their main dish. Also, Italian Radio Telescope joined to the EVN network, that is the European WBI network. The Italian WBI network, that is the 3 telescopes can make WBI among each other. And also there is the ET WBI, the East Asia to Italy Near Global WBI network. Time, SRT time is managed by 80% by INAF and Italian Space Agency for 20%. And mostly it is allocated for single-dish observation, Italian WBI, and ET WBI projects. This is a time which has passed, which needs to go through a time allocation committee, and the other time, which is the other operating time, is for a quarter, is EVN, 25%. There is also part of the time, 5% of this director's discretionary time, and also maintenance. The remaining, as I've told before, it is Italian Space Agency time. Well, how can be run operations? Operation can be run in service mode. That means that are run by an operator. This is for EVN observations. Also, it is possible to have guest mode operation. That is, for example, observers projects approved by time allocation committee are run by observers which on site directly from the SRT control room. There is also a third option, that is the remote guest mode, where observers run observation remotely, but there is an operator on site. This last mode was expected to be implemented in a later time, but unfortunately because of the pandemic, we had to speed up our operations in order to let the observers complete their projects. There is a critical issue that we have only a single operator hired for service mode. But thanks to scientists and technicians, we can run service mode because they give some of their time on duty. Observer can submit a proposal through the web portal radiotelescope.inaf.it. Call for proposal are released twice a year, generally in March and September, but target of opportunities and direct DDTs can be submitted at any time. Well, when a proposal are evaluated by the time allocation committee, a project friend is assigned to each approved project. The project friend can give support to the observer, and also give the observers the training needed to run the telescope. Also, Project Friend can give hints how about which is the best configuration, which is the best observing strategy. It is a sort of it is a person who make easier observations. There are also many tools that in supporting observers and scientists to prepare observations. We have Castia, a source visibility. Castia means look in Sardinian. A Pulsar time calculator, a schedule generator. Also, we have also meteo forecasting in order to give forecast through numerical weather through numerical model on time scale of 36 hours. This is to allow dynamic scheduling, which is so far not yet implemented, but we expect to implement it in the future. We have also some data reduction tools. For example, a single dish imager, other software for spectropolarimetry, and also single dish tools and format converters to other formats. Well, now we give a glance to SRT. SRT is a primary. SRT has a 64-meter parallel mirror with active surface. Its configuration is Gregorian shaped, and it has 6 focal positions with frequency agility. Frequency agility means that the receiver can be selected in a very short time. It's an order of minutes in the worst case. And so far, SRT operates from 300 megahertz up to 26.5 gigahertz. Azimuth and elevation slewing speed is pretty fast for a big telescope, which is about 51 degrees per minute and 30 degrees per minute in elevation. It has unique features. Sorry. These unique features are, first, the active surface, the shaped profile, the LP band receiver, and the K band multi-beam receiver. Sorry, it's good. Active surface, it is the mirror is made of more than 1,000 about 1,000 panels, which can be moved by means of mechanical actuators. This changes the shapes, the attitude of the panel, and in this way it is possible to recover the ideal shape of the telescope, as the telescope deforms itself because of gravity or thermal effects. The result is that the telescope has the same efficiency at all the elevations. For example, you can see in this plot on the left, we have the gain curve, that means that it is proportional to the efficiency as a function of the elevation. It is without active surface. It can be seen that there is a peak at 45 degrees, and the other elevation drops down to about also a tenth of its efficiency. On the contrary, on the right, you can see the gain curve, the efficiency as a function of the elevation with active surface on. It is flat. It is flat. On the bottom, there is the 7.2 gigahertz frequency, and it's very flat. That means it's constant, stable. Also, the beam, that is the point spread function, it is stable during the observation. That means we can have better sensitivity with the same observing time, and also good performances deconvolving the beam, giving high dynamic range. Shaped surface. Well, shaped surface, it is that the profile of the primary and the secondary mirrors are not analytical, are not curved, calculated in an analytic way, but they are the solution of the electromagnetic equations in order to optimize them, to avoid the blockage, which decrease the efficiency. Also, another effect of the shaped surface is that standing wave, there are no standing waves between the optics. Other telescopes can have standing waves that are ripples, that give ripples as a function of the frequency. With the shaped surface, the ripples are quite cancelled, almost cancelled. Another receiver, it is another important thing, is this LP band receiver, which is a unique combination of ultra broad frequency coverage from that goes from 300 megahertz up to 18 from 1,800 megahertz. It is not continuous, but there are bands between this range. But it's important that the low frequency end is about 300 megahertz. And also it is a unique sensitivity, has a unique sensitivity to pulsar observation, giving it can be an outstanding machine for gamma ray burst science, for example, follow-up, and also gravitational wave science. Another important feature, it is the K-band receiver, which is the receiver which goes from 18 gigahertz up to 26.5 gigahertz. You can see on the right, these are the beams, the 7 beams projected on the sky. And it is together with digital backends has a very high sensitivity for in order to make good surveys for spectral elements, chemical elements, and also for star formation lines. Okay, this summing up all the receivers. The receiver available, apart also other than the 2 receivers that I've just mentioned, there is the C-band receiver, which goes from 5.7 gigahertz up to 7.7 gigahertz. There are other 2 receivers which are being built. It is a C-band receiver and the S-band multi-beam receiver, this is in primary focus. Backends are the recorder, which is we have a total power, a total power recorder, 2 spectrometers, which is X-Arcos, which has a high spectral resolution, and also Sardinia ROS2 based spectral polarimeter, which can get up to 2.3 gigahertz bandwidth. There is also Pulsar backend. Sardinia can also work as a Pulsar backend together with the digital filter bank for Pulsar observations, and also the ROS1 backend for Pulsar observations. A brief summary of the frequency of the three telescopes, the radio telescopes, as a function the bandwidth as a function of the bandwidth as a function of the frequency. Typical, sort of just a slide for the performances. It is one of the most important things, the sensitivity, which is of the order of 1 millijansky within seconds of integration time. And beam size depends on, obviously, on the frequency and it goes from 1 degrees up to 1 arc minutes. This at 20 gigahertz. Sample time with spectral polarimeters, we can get down to 10 milliseconds, or in case of pulsar mode, 100 microseconds. But it's important to say that one important thing is that single dish are important to observe large angular scales. For example, interferometers are sensitive to a range of angular size between the resolution and also the maximum angular scale, which is due to the shortest baseline. In single dish, minimum separation is 0, so in principle they can recover the total flux of extended sources. Also, observing strategy is important. We can do on-the-fly mapping. On-the-fly mapping, data are continuously acquired while the telescope is moving, recording the pointing direction. This way, extended sources can be covered, mapping large structures. You can see this this is a scheme that describes an OTF map. The telescope, the arrows mean the direction of the scan. So they cover a map going forth and back over the world region. Here, to speed up mapping, there is a good help from multi-beam. In this on the right, we can see the K-band multi-beam, which can, for example, in a few scans, can cover a world map. This is the circle represents how the beam are projected on the sky, and the strip how it moves across the area. Yes. Okay. We go ahead with just a brief sort of short summary of what science and technology we can do with SRT. For example, there are some papers, map, for example, Battistelli and other found stronger evidence of AME mapping the flux density of M31. Also, Loro and other investigated the supernova remnants. Also, single dish imaging, it is one of the research topics which are giving results. For example, thanks to Egron, Loro, and Pelistoni, which mapped many supernova remnants with SRT at the different with different receivers, for example, LC band and K band receivers. Another important topic is microquasars, observing microquasars during outbursts, and this is made by Egron and other, with both single dish and WLBI observations. Also, GRB afterglow radio, it is one of the topics that are giving that has given results in the recent time. Another important thing, it is searching for low gravitational waves. This is important to say that SRT is part of European Pulsar Timing Array, and this array is made of the largest radio telescopes in Europe. That is Effelsberg telescope, the Nancy Westerbork, the Jodelbank telescope, and also Sardinia Radio Telescope. This it is there is then also the large European array for Pulsar. It is a sort of Pulsar WLBI interferometers. They observe simultaneous observation at all the telescopes, all the 5 telescopes, recording baseband data at each telescope and combining data, baseband data to form a phased array. LEAP has a sensitivity, it is about it's like 194 meters. Another research topic, it is the search for extragalactic masers. For example, in a group of dwarf galaxies through single dish and WLBI, single dish with SRT and WLBI observations. Another topic is made of fast transients. This is it is for example, this result on the left was made by Pilia, Bourget, and others. It is the lowest frequency detection of a fast radio burst. Also, young magnetars, bursts from magnetars can be investigated in this, for example, this paper from Esposito and other. Other observations of radio galaxies, for example, from Murgia, Brienza, and Macani. These combined also data from data between SRT and low-far data, also with comparison also with Mercat, this project. Galaxy cluster is one of other observing topics from Govoni, Vacca, and Loi. This together with other projects made also opportunity to study the magnetic field and in intracluster environment. Another, I go ahead with this project, which it is aimed to observe also the dish, the sun with SRT, the other INAF radio telescopes. It has space weather applications. It is in order to look for significant spectral variation of the solar active regions. And this is led by Pelistoni together with other researchers. It's important also the technological development. This is a Sardara. It is a ROS2 based digital backend, which has developed at the Cagliari Observatory in the Casper Consortium, and also thanks to the fundings of the regional government, which through the law that give funds for research. SRT is also involved in European surveillance and tracking of the space debris. This is a configuration which uses SRT as a receiving station of a bistatic radar, where the transmitter is 20 kilometers far from the telescope. And it is aimed to track LEO debris, LEO orbit debris. This is radio. This is another activity that we are monitoring radio frequencies interferences. We have a van that is aimed to search for interferences. It moves around in the neighborhood of the telescope, searching which the interferences that disturbs the telescope. This is a very critical issue. RFI can destroy the quality of the image, and also a good receiver. A receiver would be good, like the LP band receiver, would be useless if there were so many interferences which are much stronger than the signal we expect to observe. Another important development, another research line, it is the research for a receiver. For example, this is a C-band cryogenic phased array receiver, which is being studied by a group in Cagliari together with INAF, with SRT group, and also Toro Vergata in Rome. Metrology. Metrology studies the formation of the optics. This is important to allow high efficiency in terms of gain and pointing. When at high frequencies, the telescope is more sensible to the deformation, and pointing becomes critical. In this way, through holography and also finite element analysis, we got a good measure of the surface of the main mirror. In this way, we got an RMS of 250 microns, which is good to work up to 100 gigahertz. Or also, FEM can give us information which are the effects of the deformation on the pointing. Okay, here I'm involved directly in the control software development, which is developed by Discos team. Discos team, it is a group led by Andrea Orlati, which is at the Institute of Radio Astronomy in Bologna, And also together it is a common control software for all the 3 radio telescopes. So this is important because this way we can use the different. It is more easy for the observer to have the same interface in all the radio telescopes, in all the Italian radio telescope. It is based on ALMA common software, which is a framework which is being used also for other experiments. Well, now I've talked about the present. I'm briefly going to describe what's going on in the in the future. It is also the present because this upgrade is being working now these days, and SRT applied for tender upon tender, ricerca e innovazione, and got fundings for enhance the infrastructure. In order to this project, the enhancement is to provide the SRT to high frequency receivers and to go to 116 GHz receivers. The project involves 4 observatories: Cagliari, Institute di Radioastronomia, Arcetri, and Catania. And the duration of the project is 32 months, starting from the 25th of June to 2019. So it's the present, it's not the future. It is divided in 9 work packages. We call Obiettivi Realizzativi. I don't know how to translate in English, but okay, we say work packages. And one, it is a W-band multi-beam cryogenic receiver from 675 to 116 GHz, a Q-band from 33 to 50 GHz, volumetric camera. This is another camera from 80 to 116 GHz. There is also a 3-band coaxial receiver for all the 3 Italian radio telescopes. That is, this project is not has a part also. The POM project has a part also. This receivers was also to Monoto and Medicina. There is a metrology system for SRT that, in order to allow to observe at such high frequencies. Backends, mechanical interface, HPC and storage, and also upgrade of the laboratories. Here it is a summary of all receivers that are going to be installed by 1 year. We have the yellow are the receivers which are already working, which are already installed. I don't know which color is it. The green azure color. It is there are 2 receivers which are going to be which are being built outside the PON receiver. The purple are the rose purple. What color is it? It is there are the receiver which are in the PON project. That means that SRT is going to be upgraded from. It is going to work from a very wide range of frequency, from very low frequency that are 300 megahertz up to 116 gigahertz. I've just told in a previous slide that the importance of a multi-beam. SRT will be provided of 4 multi-beam receivers. This is important, as I've told just before, to speed up mapping opportunities. Well, this project, this upgrade project, will give a good opportunity to the community to study new science topics. We have, for example, complex organic molecules, and also it's important to survey large areas of the sky, and both in continuum and broadband spectropolarimetry. Also, having 3 coaxial receiver, millimetric receivers in the 3 radio telescope, Italian radio telescope, it's important to join all our telescopes in the millimeter global network. This is one of the last slide. It is my final slide, and it is just some important thing to say, that it is important to have multi-wavelength synergies. Many projects have been requiring coordination between facilities at different wavelengths. We have already a project that needs for radio, simultaneous radio, optical, for example, also X-ray observatories. And coordination, it is between these facilities is critical. That means new efforts must be put in order to overcome differences between these wavelengths. Not always is easy to make each other understand. For example, sometimes also terms are different, and also but it is important to put this efforts. This is a little step. SRT is inside the optical radio pilot program. We're giving ours to this project, the European project, which has started just last month. And in order, the aim is its aim is to harmonize the observational methods for ground-based optical and radio astronomy instruments, in order to give a better access to a wider range of facilities. That's all. This is my talk. Thank you very much.